Hi, Professor Ding. We can start now.
Now is the time. So today I will I could just give them a short introduction of myself. My name is Mingfa Ding, and I'm working in the Central University Finance and Economics. And actually, we are part of the organizer for this conference. So today I will be the chair for this session. And so the session is about asset allocation and climate change. Today we have 3 papers to be presented. So so for each one, I have to also be noticed. Each presentation will be 20 minutes. And so the 10 minutes Q&A will be after the presentation. So, and the presenter can see the chat box and then can answer the questions for each one. So, I also will time the presentation. So 5 minutes before the time, I will give the notice or sign and let you know you have only 5 minutes left. So, and okay, now we will start the first one, and it's the topic is the climate change and the long horizon portfolio choice, combining theory and the empirics. So the presenter is the Xander. So now let's give the floor to the Xander. So thank you.
All right, thank you very much. So let me share my screen with my slides. And then hopefully you can all see this now. All right, so thank you very much for having me here today at GRASFI. So I am honored to kick off this session. Actually, I presented this idea when it was very early stage 2 years ago at the GRASFI PhD workshop. So I'm happy to return to this place now when it's more mature. So today I will talk about climate change and long horizon portfolio choice. And we focus especially on this long horizon because of the uncertainties that we get when we want to make longer horizon forecasts on asset returns. And to do this, we combine theory with empirics, and I'll talk a bit more about why I think that's a good idea in just a few slides. So this paper is written together with my promoters, Mathijs, Cosemans, and Mathijs van Dijk, all from Rotterdam Erasmus University. All right, so let's think about this long horizon and climate change. And to do that, I would like to kick off with a quote from Robert Stembaugh from the New York Times a while ago. And he essentially says, expand the horizon to the next several decades, and the possible effects of global warming range from negligible to catastrophic. So I think even in the time after this quote, it was clear that it's not negligible, but this does highlight that there is a lot of uncertainty about what will happen with climate change in the next few decades. And this uncertainty is present at a few different levels, for example, about how climate models work. So what can we expect for climate change in the future? But also, and that's the focus of this paper, how climate change should affect asset prices. And on this second topic, there are a few issues that if we want to make long horizon forecasts, we kind of have to get around. So first of all, if you want to make forecasts for a long horizon, you want to use a long sample of historical data. But then the issue is that we only have a relatively short sample in which people actually care about climate change. And in this sample, there are a lot of demand distortions, as we call them, which is in itself good. So these are people demanding more ESG assets and those type of things, but they kind of distort what you would expect for the future if you just want to extrapolate your data from the historical data there. Then also there's an availability of disaster data. So if we look at the historical disasters that have been driven by climate change, this should not be comparable to what we would expect in future if climate change continues and worsens. And then there are more uncertainties around estimation of the parameters and those type of things. So in this paper, we will work on this uncertainty issue, and we try to get around that by taking an additional point of information, which is a theoretical model. And for this, I would like to go to a second quote, which is by Efremov and co-authors. It's an RFS paper from 2018. And they say asset pricing theory could provide additional guidance about important aspects of the return process for which the sample evidence is not particularly informative. So we would argue that climate change and finance is exactly at this point. We have sample evidence, which is some historical data about climate pricing, and more of that is coming out every day, of course, but it's not informative enough to make very long-term forecasts yet, and to really give guidance about what you should do as a long-term investor. So what we do in this case is that we address this uncertainty by including this asset pricing theoretical model by taking a Bayesian estimation procedure. So we essentially take data that's out there, but we combine it with another set of information, which is a theoretical model about how climate change should be priced. And this theoretical model that we use is the temperature long-run risk model by Bansal and co-authors from 2019. And in this model, we have the ability to account for physical climate risk. So this is only focused on physical risk because the model is driven on disasters, and those are physical disasters. So we cannot really say anything about transition risk in this setting. But by including this model, we kind of take into account theoretical views about how climate change should be priced for our forecasts for optimal portfolios. All right, so where does this fit in the literature? Well, essentially there are two streams, and I think the first one is where most of you are familiar with. So I'll be relatively short about that. There's more and more coming out about climate change and, profitability, stock returns, uncertainties, the impact of temperatures on markets, and those type of things. And we add to this literature in that sense. And then the second aspect is long horizon risk and portfolio choice, which is a literature that looks at what the differences are between investing for short term and for the long term. And one clear example there is, for example, if you have returns nowadays and you expect that over a longer horizon there will be some mean reversion, so that means that high returns now can be followed by lower returns later, then that would make long horizon investors less risky because shortcomings now can be offset by future higher returns. And these are differences between long and short-term investments, and we will look especially at how climate change affects those aspects of long horizon investing. So again, the methodology in a nutshell, now a bit more theory or more details. So what we do, we forecast essentially stock returns, returns on the market portfolio, but also on the risk-free asset and a few of those things. And we do that by taking normal data that you would use for that, so price-dividend ratios, for example. But we also include a proxy for climate change, which is the temperature anomaly in its setting. And by taking that proxy for climate change and using this Bayesian setting, where we also have prior beliefs about what this temperature anomaly should do for the future returns, we allow for differences in beliefs in what we get in our outcomes. So we allow for an investor that believes in this theoretical model, and we also allow for an investor that just wants to look at historical data. We apply this to initially the market portfolio and a riskless bond asset to check how you should divide your assets between those two for the long term. But we also look at vulnerable and non-vulnerable portfolios, which are portfolios that are especially exposed to temperature change in historical data. So this model that we're talking about, so I've mentioned it a few times before. Let's get a bit more into detail without any equations here, but I welcome you to read the paper by Bansal and co-authors, of course. So they introduce a temperature long risk model. And essentially what they are doing there is they combine climate change and economic growth by saying that climate change impacts climate disasters that will occur more frequently when temperatures rise. And in that case, when you get this climate disaster, then consumption and dividend growth goes down, and this has impact on current asset prices. So climate change becomes a currently priced long-run risk, even if those disasters have yet to materialize in the future. But because we already expect future disasters, we see this in current prices. So this is the model from which we take prior information. So we use this to estimate our vector out regression model with. And as a benchmark, we then use the normal long risk model that is frequently used in the literature by Bansal and Yaron in 2004, where there's also a persistent long-run risk, but there's no climate-related aspect in there. So we compare how these two different models have different implications for long-term investors, and that will kind of show us how much impact climate change has on our investment portfolios. So let's look at those models first. So this is quarterly data from 1947, which we actually use for our estimation. And as you can see, both the long-run risk model and the temperature long-run risk model are able to match many of the data moments well. And especially the temperature long-run risk model does not seem to perform worse than the normal long-run risk model on many of the general benchmarks for these type of things. So we match the equity premium relatively well. In general, we have somewhat too low price-dividend ratios in our simulations. But this is a general problem with the long-run risk model that is also in the temperature long-run risk model, but not too much related to, or it's not because of this inclusion of climate change. And then what we have new in this temperature long-run risk model is that we have, we also try to match the expected temperature anomaly and the standard deviation of the temperature anomaly. And here I want to point out that especially this expectation is far off. So this volatility we actually match really well, but we're not able to match historical temperature anomaly levels in the model. And this is simply because the model is structured in such a way that temperatures increase well, quickly in the beginning, and then they flatten off towards this future level. While in the data, we actually see that the temperatures were relatively low and stable at the beginning, and then in the end of the sample, they are quickly increasing. So the average temperature level here, we just cannot really match. Okay, so what do we get? So we now have this vector autoregression model where we take market returns and risk-free returns, and we regress those on price-dividend ratios, the risk-free asset in the previous leg, and the temperature anomaly. So I want to look at first, well, the data. So this is just the historical data from the 1950s, and see what that kind of implies for our results here. And mainly want to focus on this last column where the temperature anomaly is used as a predictor. So we have the market returns here, and what we can see is that in the data, we find that the temperature anomaly has positive impact on market returns. So it's not significant, neither all of these things are insignificant, which is kind of the point, right? So we started saying that there's simply not enough information to make reasonable estimates about climate change with just historical data. So to increase the estimation precision, we combine multiple data sources, which is especially what we do here, but these are not significant on its own. So this point itself, 0.009, it may look relatively small, but what it implies is that if you have a temperature anomaly of 1 degree Celsius, then the market return will be 0.9% higher per quarter. So this is economically extremely meaningful. And especially if you look towards the future with temperature anomalies increasing, this can become a very large force. And then in the model, and this is actually not surprising in necessarily, but we see that the market actually performs worse when temperatures start increasing. So in the model, we have temperatures going up, and then we draw more and more of these climate disasters, which then affect returns and economic growth. So we actually find that with increasing temperatures, the market returns go down. And this difference between the model and the data is really big as well. So this difference here implies that if we have a 1 degree Celsius increase in temperatures, then the model has roughly 1.5% less market returns per quarter. So this is a major difference. Even though we don't have anything significant, this will have a lot of impact on your asset allocation. And if you believe these type of things to have impact on asset prices, it may be worthwhile to include this in your models. So let's look a bit further. So we now make forecasts from these VAR models, and we forecast up to 100 quarters ahead. So we look at 25-year portfolios. And first we look at what does this imply for the variance that we get in our forecasts, and what does it imply for the returns that we get in our forecasts. And then we move to how this combines in an asset allocation. So we have 4 different models. So one is the database model only. Then we have the which is the red line here. Then we have the longer risk prior, which is just a theoretical model. And then these 2 dotted lines here, they are combinations of a theoretical prior with the historical data, where in the blue one, we combine this temperature longer risk model with the data. And in the green one, we take the normal longer risk model as a benchmark. So what we find is in the data, we have a lot of mean reversion. So this is what I was talking about before. So current high returns are usually followed by lower returns in the future. So if you hold your stocks for longer, then you'll have in total less risk because you have this mean reversion. Actually, our model implies that we have a lot less mean reversion. And this is the case because when temperatures are high, we tend to draw a lot of these disasters after each other. So when temperatures get high, disasters happen in clusters. So one negative return is followed by another negative return, which takes away a lot of this mean reversion. And in total, we actually find that overall, if you include this temperature longer risk model, over longer horizons, we get a lot more risk in equities than we had if we looked at the normal longer risk model or just the data. So by including climate change in our setting with this model, we find that equities become riskier, especially over the long term. So what happens in returns? Well, if we just, in the interest of time, just focus on the dotted lines and compare the temperature longer risk model, the combined in a Bayesian setting with the normal longer risk model, we find that overall the risk premium, so this is the quarterly risk premium, is always higher over every horizon in the temperature longer risk model than in the normal longer risk model. And this is essentially because we have included more risk in the model. So in that sense, we also make higher expected returns because the model rewards fairly for this risk. So over every horizon, we have higher returns. But as we remember from the previous slide, especially in this longer horizon, we start to get a lot more variance if we include climate change in our model. So how does this end up in the overall asset allocation? So now we look at this portfolio where we hold our assets for up to 25 years. All right, thank you. And if we just compare these blue and green lines again, we find that if we initially, for relatively short-term investments, take climate change into account, the variances aren't too different yet. So the risk conception that we have is roughly the same for equities, but we have higher returns when we account for climate risk. So in that case, we invest more in the market than we would if we were just to not account for climate change. In the long run, this actually changes significantly. So we get a lot more risk because we include climate change, and we start to invest a lot less in the market compared to this green line where we don't have climate change in the model. And this effect is really significant. So it's almost 1/3 less that you would put in the market compared to with the alternative being the risk-free asset if you invest in the long run and account for climate change in our setting. So this is really a big impact. So climate change in principle has higher returns or results in higher returns, but especially in this long run, a lot of extra risk. So then just to go briefly over this, we also did an analysis on vulnerable and non-vulnerable portfolios that were exposed to temperature change in the historical sample. And we find that in general, the differences between those vulnerable and non-vulnerable portfolios are a bit smaller in the data and the model because they tend to be affected roughly similar by temperatures. But for example, vulnerable portfolios get just hit a bit more by disasters than non-vulnerable portfolios. However, overall, if we look at our Bayesian setting, this is still economically meaningful. So this Bayesian setting implies that the vulnerable portfolio has roughly 0.3% more returns per quarter based on the temperature anomaly, if the temperature anomaly would be 1 degree Celsius. So what is the result we get from that in our asset allocation? Essentially, we find 2 opposite results for the data and the model, which is where it becomes really interesting to include what your beliefs are, right? Because we essentially say we have either historical data beliefs or a theoretical model, and it's kind of up to you to make a weighting between what your beliefs are if you're an investor. If we look at this historical model, so that's the black line, we find out that we initially start investing a lot in this vulnerable portfolio, which tends to be fairly compensated for this additional risk. So it kind of makes sense. And in the long run, we shift to the non-vulnerable portfolio because it becomes less risky in the long run when we draw more disasters that have less impact on this non-vulnerable portfolio. For the data, we find the opposite. So we initially start investing in these non-vulnerable assets because they have higher returns in the historical sample. But in the long run, because the correlation between those portfolio changes as well, we start buying into this vulnerable portfolio from diversification perspective. And our Bayesian setting is roughly in between. So here it really matters for what your optimal investment would be if you compare either green and brown investments or vulnerable and non-vulnerable investments, what your beliefs are. All right, just to conclude, we argue that climate risk is particularly relevant for long horizon investors if you are to include different uncertainties that you get over longer horizons. And our temperature long risk model that we use to take climate change into account gives higher but riskier long run risk premia. And that implies that in the short run, we tend to buy more equities. But if you're a long-term investor, we suggest with this model that you would buy less equities. And the prior beliefs you have significant impact on the optimal allocation that you would give to vulnerable and non-vulnerable portfolios. So it's important to take into account how your beliefs are around those type of assets. All right, thank you very much. I look forward to any comments you have.
Thank you so much. Exactly 20 minutes. So perfect timing. So we can see anybody have a question on the chat box?
Actually, if there aren't any, I have one.
Yeah, you guys can ask. Oh, yeah, I have many ones.
Maybe I let the question in the chat be answered first, then I can add it if there's time.
All right. So thanks for the presentation. I'm assuming that the normal long risk model doesn't include any climate related information. Yeah, that's true. So this model doesn't have this temperature anomaly also as predictor. So it's just kind of like agnostic about climate change. And the calibration exercises are in US data. So our market portfolio is essentially the S&P 500. And we use US short-term bonds for our bond portfolio.
Okay, I will jump in, even though my video was stopped by the host. So again, thanks for the presentation. I think it was very interesting. I wanted to simply ask, maybe this is something I missed, but how does one define vulnerable versus non-vulnerable assets here? Is it just a stylized category under which you would say, you know, certain companies are going to be vulnerable, but you stay away from this definition? Or, I mean, perhaps this is more of a comment, but you can think, for instance, one company that is not doing any business in, let's say, oil or anything that's going to be physically affected from climate change, but because of their location, if they're located in Florida, for instance, they might be affected by a lot of the you know, side effects of climate change, so to speak. So how does one think about it? I would be interested in hearing about that.
All right. Yes. Thank you for the question. Yeah, we've actually spent a lot of time on these portfolios. So what we have here in the model is where we simply in the theoretical model we simply say that a disaster has less impact on the vulnerable portfolio than on the non-vulnerable portfolio, which is kind of more impact, which is kind of obvious to include in that way. In the data, we do kind of a typical asset pricing approach where we simply take a rolling regression of all firms in the US and we regress this on the market factor and some other things. And then we take a loading that they have on historical temperatures. And based on the kind of the impact that temperatures have on historical returns, we sort these firms. So then we get these vulnerable, non-vulnerable assets. So we've been working on also options to do this based on exposure. So I guess for you, it would be a logical suggestion to use carbon measures or something like this. But then the issue is usually the time horizon. So we have a relatively long sample because we try to forecast 25 years ahead. So if we were to only use relatively short data sets. Like we have data about carbon emissions for the last few decades, but it's just simply not enough to really make these long-term forecasts with some precision.
I actually wouldn't recommend carbon emissions either for the same reason, because so the way I think about climate risks going into really long horizons in the future is that carbon emissions are the news from the past. So what's going to happen to carbon emissions in the future seems to be more important for your model and therefore your calibration. I think going in the forward-looking information direction is the right thing to do. Having said that, I don't know what setting might be the best here. If I think about anything, I will let you know for sure.
All right, thank you so much.
Okay, it seems that there's no more question. Okay. And okay, now it's also for, I guess it's 30 minutes, so it's okay. We give to the second presenter. And okay, the topic is the sea level rise and the portfolio choice, and the presenter will be Emirhan Ilhan. And so let's give the floor to Emi. Okay, thank you so much.
Yeah, thank you for the introduction. Again, my name is Emir. I'm a PhD student from Frankfurt School, and today I will be talking about household portfolio choices and how they might be affected by physical climate risks. And specifically, I will be talking about sea level rise. Perhaps it's not very necessary to motivate the paper in this audience, but I'll just go over it very quickly. So globally, sea levels are expected to be as high as 6 feet or even higher by the end of the century. So that's about 2 meters or so for the metric system. And the rate of sea level rise currently tracks the worst case scenario laid out by the Intergovernmental Panel on Climate Change. But perhaps even more importantly, the rate of sea level rising is accelerating due to carbon emissions that have already been generated. So this is going to be an issue that we're going to face even if as a world we're going to meet a net zero target. So to put it into perspective, a 3 feet sea level rise scenario will permanently flood areas currently home to about 2 million people in the US. And a 6 feet scenario would do the same to homes of 6 million people. But on top of this, coastal communities are also vulnerable to temporary flooding due to chronic tidal events and extreme weather events such as hurricanes. And echoing these concerns, you can see sea level rise related news in the mainstream media quite often. And if you look at the search volume index on Google Trends for sea level rise, you can see a clearly going uptrend in public's attention to sea level rise. So when I think about how sea level rise might affect housing, I think of two primary physical channels. The first one would be the slowly rising oceans that will eventually and permanently flood coastal areas. And the second one would be the more severe and more frequent extreme weather events such as storm surges, hurricanes, nuisance flooding that are correlated with rising sea levels. Now, both of these physical channels can adversely affect home values and therefore the housing wealth of households. In fact, there are some papers in the literature that already look at these. But importantly, both of these channels also have substantial uncertainty about them. So permanent flooding in terms of its timing and how it's going to manifest itself is super uncertain, as scientists frequently update their forecasts with new findings. And extreme weather events also have inherently high uncertainty in their expected costs, timing, and frequency. So how does this tie into household portfolio choices? Well, it is a pretty established fact now in the household finance literature that owner-occupied housing is the largest asset class for most of households. And value of these real estate assets are inextricably linked to the land they're built on, and therefore they're exposed to sea level rise risks. Now, when you think about financial markets, one of the primary duties or responsibilities of these markets is to provide instruments to hedge against risks so that risks are transferred to people who can bear these risks the best. But when it comes to sea level rise or physical climate risks in general, it's not very clear that there are instruments that actually allow you to hedge against these risks, which is one of the points by Engel et al., where they say individual investors are largely constrained to self-insurance exactly for this reason. In the US, home insurance is mandatory, but it does not cover flooding events. And there's a flood insurance market, but I argue in this paper that it is insufficient because the coverage is low and the premiums are not fixed. So whenever there are more flooding events, the premiums actually hike. And for whatever reason, the take-up rates of flood insurance policies is very, very low, even in areas where houses are at great risk. So in this paper, combined with the illiquid nature of housing markets, I argue that sea level rise risk constitutes an undiversifiable background risk. And the theory tells us that background risks under general conditions on households' utility functions make households less willing to take other types of risks, such as financial risks. Now, I see that my paper contributes to two distinct literatures. The first one is what I will call the growing climate finance literature, where people have looked at how climate risks interact with real estate markets and financial markets. And it also contributes to the determinants of portfolio choices literature, where people have looked at things like labor income risk, human capital risk, and entrepreneurial risk. To my knowledge, my paper is the first that connects climate risks to household portfolio decisions, especially physical climate risks. And I will do this by showing that sea level rise exposed households participate less in the stock market and therefore leaving the positive equity premium on the table. Now, in case I do not make it in time by the end of the presentation, here's what I find. I find that compared to unexposed homeowner neighbors, sea level rise exposed homeowner households have a lower propensity to participate in the stock market. They hold a smaller share of financial wealth and risky assets, and they're more likely to exit from and less likely to enter into the stock market. As a placebo test, I look at renters that have no home equity whatsoever, and I do not find any effect of sea level rise exposure on renters, which corroborates a home ownership channel. Then I look at staggered adoption of state-led climate change adaptation plans, which plausibly reduce the uncertainty about the effects of sea level rise exposure on households. And I find that following these plans, households' willingness to take financial risks actually increases. Last but not least, in my final analysis, I show that the effect is driven by long-run sea level rise risks as opposed to short-run risks, and that the effect between household market participation and sea level rise risks is elevated at times when households' attention to climate change is aggravated. So the household survey data I use in this paper comes from the panel study of income dynamics. Specifically, I used 10 waves between 1999 and 2017, which is collected every 2 years. And I start to sample from 1999 because the question about stock holdings was first divided into individual retirement accounts versus non-individual retirement accounts in 1999. Importantly, I used restricted PSID data, which includes zip code information and census block information, which is at least important for at least two reasons. The first one would be that it allows me to minimize measurement error in the construction of the sea level rise measure by computing everything at the census block level. And it also allows me to compare households within the very similar neighborhoods, such as within the same zip code. And the choice of outcome variables is motivated in the paper by Janati and Wang and Brunamaya and Nagel, where I look at a dummy of equity participation, so 0 and 1. I look at the financial wealth invested in risky assets, so risky share. And I also look at the household stock market participation dynamics as an entry into and exit from the stock market. So the sea level rise data comes from the National Oceanic and Atmospheric Administration, which provides sea level rise maps with 1-foot increments. The process that generates these maps takes into account of ground elevation, local and regional tidal variation, hydrological connectivity, as well as man-made features such as pipes, bridges, and seawalls. It does not take into account, however, vertical land motion, which was the criticism made by Murphy and Spiegel in their paper. So you can think about a sea level rise exposed household being exposed to this risk because sea levels are rising, but it might also be that the ground is shifting beneath you and going down, right? So that's what vertical land motion means. And to account for this fact, I recreate the vertical land motion component of the measure that they propose and add it as controls in my regressions. I also add elevation and distance to coast as variables in my regressions, as they may be correlated with housing amenities such as beach access, improved views, and so on. So this map shows the geographic dispersion of sea level rise exposure in the US. As you might expect, places like Louisiana and Florida are very affected. So the Gulf Coast has the most risk in terms of these physical risks, then followed by the East Coast, whereas the West Coast is relatively protected by from these physical risks. And in this map, I show the neighborhood around the TIAA Bankfield Stadium, where Jacksonville Jaguars NFL team play their games at. And you can see that there's also a lot of local heterogeneity in the measure that allows you to capture the effect to a greater extent. So in the paper, I start formally by investigating the relationship between sea level rise exposure and the dynamics of household stock market participation for homeowners. Importantly, in all the regressions, I include zip code by year fixed effects, which means that the identifying variation in these regressions comes from the comparison of homeowners in the same zip code, but with different levels of sea level rise exposure after controlling for a lot of different household and geographic characteristics. And because stock market participation variables tend to be very sticky, I cluster standard errors at the household level. Before I go into the results, I also would like to mention that these are the control variables I use because they're not going to be appearing in the tables. So I include things like age, marital status, financial, race, family size, as well as educational attainment. And there are other financial variables such as the total income of the household, the wealth of the household, the house value, home insurance, as well as the geographical variables that I talked about previously. Now here are the baseline results. So as expected from the economic theory, sea level rise exposure does seem to be a background risk for households, as comparing homeowners within the same zip code, households with higher sea level rise exposure actually have a lower propensity to participate in the stock market. They also hold a smaller share of their financial wealth in risky assets, and they're less likely to enter into and more likely to exit from the stock market. Now, these effects are also economically meaningful. For instance, one standard deviation increase in sea level rise exposure decreases the propensity to participate in the stock market by about 1.8 percentage points, which corresponds to about 6% decrease because the mean participation rate in the sample for homeowners is 30%. The same shock increase in sea level rise exposure decreases the financial wealth invested in risky assets by about 1.6 percentage points, which corresponds to about a 9% decrease in the risky share. And these are, to put it into context, similar in size to the impact of one standard deviation increase in uninsurable labor income risk estimated in Fargareng et al. And Palia et al. Now, one may argue that changes in the house prices of sea level rise exposed houses, specifically downward changes in these house prices, could generate the same patterns as opposed to the background risk channel that I was highlighting previously. Now, these things are difficult to disentangle, but in the paper, I argue that house price changes are unlikely to be the only mechanism at play here for several reasons. The first is that all regressions that I have are conditional on housing wealth and home value, which should absorb a lot of the changes in the house prices. But on top of that, zip code by year fixed effects in the regressions absorb changes in local economic conditions, including changes in regional house prices. But finally, I design a test where I split the sample based on median house price growth. And I find that the effect between sea level rise exposure and reduced stock market participation is still present in locations where people have experienced high house price growth, which implies that second movement effects of sea level rise exposure still matter for portfolio choices here. I also rule out some other alternative explanations that one may be concerned about. So you might be saying, well, maybe you're capturing sea level rise exposure, but it actually captures differences in risk preferences. I estimate the risk aversion of households in my sample following the methodology of Kimball et al., and I find that the results remain unchanged. You might be worried about endogenous choice of housing location by households. I repeat the analysis in a sample of households who never moved in the 20-year sample period that I have. I find that the results remain unchanged. And finally, from the idea that rental markets are liquid and renters have no home equity, therefore sea level rise exposure should pose little to no threat to renters, I use renters as a placebo sample, and I find that tests in this sample reveal statistically insignificant estimates, implying that sea level rise exposure is an exposure that manifests itself through home ownership channel. Now, still a lingering concern of endogeneity might remain. So 17 states in the District of Columbia finalized what are called state-led climate change adaptation plans in the US, which prepare against the adverse effects of climate change. And I use this, the introduction of these plans as shocks to households' so-called perceived sea level rise risks. Now, these plans include measures like reforming the flood insurance system, building and financing new seawalls and flood walls, promoting resilient design against sea level rise exposures, as well as introducing disclosure regulations about flooding during housing transactions. I argue in the paper that these plans signal the state government's commitment to protect the state residents and the environment. If these plans are credible signals of these commitments, then households' willingness to participate in the stock market should increase after the adoption of these plans. If they're not credible signals, then we should either observe no change in portfolio allocation decisions, or perhaps even a further decrease because plans will make sea level rise risks more salient. Now, the staggered nature of these plans do not seem to follow a predictable pattern. So you will see that the timing of these plans are not clustered geographically. So for instance, Florida, Virginia, and Maryland passed these laws in 2008, followed by California on the West Coast. Then, both Oregon in the West Coast and New York in the East Coast passed plans in 2010 and so on. And not all coastal states have finalized plans. For instance, in places like Texas and Louisiana, and North Carolina as well, where these states experience a lot of sea level rise risks, they have not passed any plans. But even landlocked states like Colorado passed such plans because these plans do not only have measures against sea level rise risks, but generally climate change adaptation and mitigation measures. So consistent with the hypothesis that I introduced, I find that following the adoption of state-led climate change adaptation plans, I find that sea level rise exposed households they experience an increased willingness to participate in the stock market compared to their less exposed homeowner households within the same neighborhood, so their neighbor counterparts essentially. And this is true even if you look at the propensity to participate in the stock market in the columns 1 and 2, or if you look at the share of financial wealth invested in risky assets. Now in the
5 minutes left.
Yeah, I was gonna say that. Thank you very much. So in these last 5 minutes or so, I want to talk a little bit more about some new analysis that I added very recently that allows me to interpret the results a little bit better. So far, I remained the effects that I'm identifying are coming from long run or short run sea level rise risks, but these two different categories have potentially different implications for households as well as policymakers, right? So the sea level rise maps coming from NOAA's screening tool aim to capture long run sea level rise risks, but these are also very much correlated with an increase in short run flooding events such as storm surge flooding, tropical storms, and hurricanes. So to get a better understanding of what is going on, I use the storm surge exposure of NOAA as a proxy of immediate flood risk. So they also provide data on which places in the US are more exposed to storm surges, which are very much related to hurricanes as well as less intense flooding events. The downside of this data is that it's only available for the eastern Gulf Coast, but it is still something. So what I do is I run a horse race between my sea level rise exposure and the storm surge exposure and try to see which ones cause the effects that I'm identifying. And when I include them in the same regression, as you can see, it seems like the effect between sea level rise exposure is due to the long run risks, as the sea level rise exposure measure loads statistically significantly and negatively in all the columns that I would expect, whereas storm surge exposure seems to be pretty much irrelevant for explaining the stock market participation decisions of households. One may also think about attention to climate change and salience of flood risks in general to be a very important determinant of this effect. In fact, there are papers in the literature where they show that sea level rise exposed houses trade at a discount when attention to sea level rise and climate change in general is high, and that low salience of flood risks might lead to low flood insurance take-up. So I designed two tests where I try to capture times where attention to climate change is high. I first use the Wall Street Journal Climate Attention Index from Engel et al. And I also use a methodology that was designed by Baldoff et al., where I look at the top 10 costliest hurricanes, and I look at the unaffected neighboring states after these hurricanes happen. So households in these unaffected neighboring states are, as the thing goes, are not directly hit by the hurricanes, but presumably their attention to flood risks and climate change in general is heightened during these times. And I find in both of these tests that whenever attention to climate change is high or flood risks is high, the effect I'm identifying between sea level rise exposure and reduced stock market participation is also heightened at the same time. Last but not least, there are some concerns people might come about. For instance, you might argue that maybe past flooding experiences are affecting the effects that you're finding, and what I'm measuring is not actually a forward-looking measure, but rather a proxy for past flooding experiences, using data on flooding disasters that happened in the past. I designed a test where I exclude people who have experienced past flooding events, and I find that results do not change. When you only look at the sample of people who did experience flooding in the past, the effect is also still there, which implies that it is unlikely that this is the case in my sample. Again, you might argue that there's a political divide in terms of party lines in the US based on beliefs in climate change, and I find that being a likely Republican or a likely Democrat is not the driving mechanism behind my results. So since I have about 20 seconds to conclude, I should do so. In this paper, I identify a unique source of background risk through a home ownership channel, which will likely become more and more important in the future. More specifically, I find that households exposed to sea level rise risks reduce their stock market participation, perhaps as a hedge in the long run. And I find that following the adoption of climate adaptation plans, which might provide signals of states' commitments to protect their residents, I find that households actually in adopting states increase their stock market participation. So I thank you for listening to my presentation, and I look forward to comments and questions in general.
Okay, thank you so much for Emirhan. And now let's look at the Q&A, where they have some people post some question for you. Yes.
Okay, so one question says, do you find stronger results when using a broader group of fixed effects such as county and state level? I would assume that in that case, there is stronger variation in sea level rise exposure compared to the zip code level. So the answer to the first part of the question, thank you for the question, by the way. So the answer to the first part of the question is, I don't remember if I find stronger results in terms of magnitude, but these regressions at the state and county level also work out the same way. So if you compare households within the same state or the same county with differing levels of sea level rise exposure, you do find that exposed houses or households rather still have a reduced stock market participation. However, I would argue that it is very important to be as local as possible, because if you look at NOAA's sea level rise maps, you will see that there's a lot of local heterogeneity going on. And to me, having a smaller sort of neighboring control group, so to speak, makes a lot of sense, because there's a lot of things that happen at the regional level that might, for instance, increase your adaptation towards sea level rise exposures. You can imagine municipalities taking steps towards mitigating these risks, in which case it makes more sense to, I think, compare households, within the same proximity of region in general. But yeah, I'm carrying on. Basically, yes, I do still find the same results at the county or state levels.
If there's nothing coming in, maybe I can ask a question as well.
Yeah, please do.
Thank you for the presentation. I was just wondering, do you find, you seem to have some data on flood insurance as well, right? Do you find differences for people who actually insure themselves or not? How does this control work out? Because I would imagine that you would have less risk. I mean, even if it's not a perfect insurance.
Yeah, thanks for the question. I think it's a very natural question that comes up. So one thing that is nice about, so this is sort of related to the question before, but one thing that is nice about the US flood insurance system is that there's indeed data about flood insurance, but these are averages at the county level. So you cannot observe whether one person has insurance or not. But when you look at flood insurance data, you can see how many policies are being taken at an individual level. But I cannot match these individuals to my sample, obviously, because both of these different data sets are anonymous. But in the flood insurance system, you can see where these policies are located in terms of county. Now, inherently, when you control a zip code by year fixed effects type of setting, you are also controlling for anything that is happening at a higher level, right? So if I were to merge county level flood insurance information to my data set, zip code by year fixed effects would absorb those immediately. So if I had data on flood insurances at an individual level, that would be the best. But unfortunately, FEMA only provides county level averages. And these county level averages, they're just not going to appear in the regression because of these fixed effects. One way around this could be to, relax these fixed effects and do a state by year fixed effect type of analysis and see how flood insurance is loaded. I haven't done that yet, but I would also expect the same. I would also expect households to have different types of behaviors.
No, yeah, it makes a lot of sense, and I think if you really take out fixed effects, it will be hard to judge the regression in any case.
Yeah,
so.
When you do that, then there are a lot of other concerns about, well, when you compare people in the same state, then it's more like a compromise story here. Like, what do you give up and what do you add?
Mm-hmm.
But I should do it. Yeah.
All right. Thank you.
Okay, thank you so much. Okay, and now we turn to the third presenter, and the topic will be climate change concerns and the mortgage lending. And the presenter is the Tinghua Duan. And now I give floor to you. Thank you so much.
Thank you. So let me share my screen first. Can you see my screen? Okay.
Yes,
first,
no problem.
Oh, thank you. First, many thanks for the conference committee include this paper in the program. And I'm Tinghua Duan from IIGF School of Management in Paris. And this paper is titled Climate Change Concerns and Mortgage Lending. It's co-authored with Frank Weikai from SMU. First, let me kick off the presentation from this NOAA picture. According to this picture, we can see the global temperatures has been rising since 1970s, and it's about 1.5 degrees in recent years. Along with the rising temperatures is sea level rise, more frequent natural disasters, and extreme weather events. So many scholars and policymakers have warned of the potential damages to the global economy caused by climate change. Recent studies explore whether financial markets efficiently price the long-run risk of climate change. And studying this research question is important because first, pricing climate risks properly today reduces the possibility of wealth transfers between the uninformed and sophisticated investors, and the likelihood of extreme price movement in the future. Policymakers also increasingly concerned about the systematic risks imposed by the climate change on financial stabilities. So here, one approach is to increase the one approach to address the issue is to increase the amount of reliable information on financial institutions' exposure to climate-related risks. So, for example, the United Nations launched a platform called Task Force on Climate-Related Financial Disclosures to provide a guidance for companies and financial institutions to disclose their climate-related risks. However, financial institutions also need to be aware of climate change in order to take actions. So in this paper, we examine whether lenders consider climate risks when originating mortgages in the US. The setting of residential mortgage market make it relevant to study the pricing of climate risks because of following reasons. First, mortgages are characterized by real estates, which are vulnerable to climate-related risks, including sea level rises, wildfires, and storms. According to the recent literature, they have found that the housing price has been priced in, the climate risk has been priced in the housing price. Second, most mortgages in the US have maturities as long as 30 years, a horizon over which climate risks may well materialize. According to our sample, there are 79% mortgages are longer than 20 years. While firms can adapt to the climate change through geographic relocation and product diversification, but adaptation for real estate is very difficult. Here, someone may argue that the mortgage owners should buy the flooding insurance if their homes are located in the flooding affected area. And if this is the case, then the major risk of the major climate risk should be borne by the insurance companies rather than the mortgage lenders. However, several reasons make it unlikely because the number of flood insurance policies and their total dollar amount have declined substantially since 2006. And second, policyholders may not maintain their flood insurance over time, as the median tenure was only 2 to 4 years. And mortgage applications are subject to the discretionary approval by local loan officers whose beliefs about climate change may affect their lending decisions. The literature has found that the lender's sentiment could influence the loan approval decisions. And finally, the mortgage is the largest component of household debt in the US and has historically related to the systematic risk. According to the industry, they also pay a lot of attention on the potential impact of the climate risk on the mortgage market. For example, the CEO, the chairman of BlackRock, Larry Fink, said that what will happen to the 30 years mortgage, a key building block of finance, if lenders cannot estimate the impact of climate risk over such a long timeline, and if there's no variable market for flood or fire insurance in impacted areas. So in this paper, we follow the large climate science literature and use the local abnormal temperatures as a proxy for public beliefs about climate change. The idea is that although the local temperature fluctuation may not be informative about the global warming trend, the people in this area experiencing the abnormal warm weather would do increase the personal belief about the climate change. And second, the temperature shocks are placebly exogenous to economy and helps making causal inference. So to do our empirical test, we first verify high local temperature leads to elevated attention to global warming and the beliefs about climate change. We first use the Google search volume index of the topic global warming to measure the elevated attention to global warming. And then we use the local climate change beliefs from the EU climate opinion maps. And the EU climate opinion maps is the survey data which provides a percentage of US adults' opinion about the climate change. And after verifying the proxy to climate change, to the belief about climate change, we further find that the high local temperatures lead to the significant reduction in mortgage origination, which is measured by the loan approval rate and the total loan amount in the county year level. And the abnormal temperatures could affect mortgage originations through the both credit demand and the supply channel. So according to the credit demand channel, the worsening local economic conditions due to the higher temperatures may drive firms or residents to relocate and suppressing the demand for the mortgage credit. However, our result is not fully driven by the changing local economic conditions and the demand for credit. we first control for the state by year fixed effect and the county fixed effect to control the time varying local economic conditions and time invariant local economic conditions. And we also control for county level macroeconomic variables and the borrower's characteristics to control the quality of mortgage applicants pool. And we also find that the results hold in counties with strong demand for mortgage credit. And finally, we conduct the placebo test using the fintech lenders, and which is my favorite part of this paper, and I will explain more details later. And the underlying mechanism of this paper is a belief channel, which lenders' rising concerns about climate change affect their lending decisions. So we further find that the negative effect of temperature anomaly on mortgage origination is stronger in counties with strong prior belief about climate change. The effect is stronger after public become more aware of climate change, and in counties more exposed to sea level rise risk. Okay, this paper makes 3 contributions to the literature. First, we as to the literature study the impact, the economic impacts of climate change. And according to the literature, there is a bunch of evidence studies the impact of climate change on in macro level and micro level. And our study implies that the climate change may also adversely affect the local economy through reducing the supply of mortgage credit in regions most vulnerable to climate risks. Our study also contributes to the climate finance literature that concerns whether financial markets efficiently price climate risks. And we show that lenders do account for climate risks in mortgage origination, but only when they sufficiently believe in climate change. Finally, our study also complements the local weather fluctuations influence public belief about climate change. And the literature has shown that the public belief about climate change is important for the potential impact of climate change on the market. We show that agents' heightened concerns for climate change affect their real decision making. And
sorry to interrupt you. You only have 10 minutes left, so okay. I think you need to speed up.
Yeah, sure. Thank you. And to study the research question, we first obtain the data about the temperature from the NOAA, and we construct the measured temperature anomaly, which is the difference between the monthly temperature and the historical average in the past 36 months. And we obtain the mortgage application data from the HOMDA database, which is a public database provide all mortgage applications reviewed by the qualified financial institutions. It contains borrowers' characteristics, loan characteristics, and the decision on the loan application. And our final sample includes 83,000 county year observations for 3,000 unit counties from 1990 to 2016. We also obtained the loan interest rate data from the Fannie Mae and the Freddie Mae loan level dataset. And we also obtained the county level data from the Census Bureau and the Bureau of Labor Statistics, as well as the Federal Housing Finance Agency. So here is the summary statistics of our sample. And we constructed the loan approval rate, which is the number of loan applications approved divided by the number of loan applications reviewed in a county year. And we can see the mean of the loan approval rate is about 70%. We also constructed the loan amount, which is the total dollar amount of originated loans that are not sold to other institutions in the end of the year at the county year level. So before doing our empirical test, we need to first verify the persistency of the local temperature anomaly. According to our argument, the local temperature anomaly should be not informative about the global warming trend. So we expect that the local temperature anomaly are idiosyncratic and unlikely to be informative about global warming trend. To test the persistency of temperature anomaly, we regress the temperature anomaly on its own lag. And we can see the coefficient of the temperature anomaly is insignificant, which confirm our prediction. So next, we need to verify that the local temperature anomaly is a good proxy for public belief about climate change. We first use the Google SVI data, the Google SVI of the topic global warming in each design market area to proxy for attention towards global warming. And our sample period starts from 2004 to 2016. And when we regress the abnormal SVI on the temperature anomaly, we find the coefficient of temperature anomaly is positive and significant, which confirms that the temperature anomaly is a valid proxy for the attention towards global warming. When we break down our temperature anomaly into 5 quintiles, and we find that our result is driven by the warmest quintile. We further use the data from the EU climate opinion maps to measure the climate change belief. We construct 2 measures. The first is worry, which is the fraction of population in a county who are somewhat or worried about the global warming. And another is timing, which is a fraction of population in a county who think global warming is already harming people in the US, now or within the next 10 years. The sample period is from 2014 to 2018. And we find that the coefficient of temperature anomaly is positive and significant, which confirm the temperature anomaly is a good proxy for the climate change belief. And when we break down the temperature anomaly into 5 quintiles, we find the result is driven by the warmest quintile.
5 minutes left.
Okay, thank you. So next, we're gonna ask, does the effect of abnormally high temperature extend beyond climate change attention and believed to affect agents' real decision making? Our null hypothesis is local temperature fluctuation will not affect mortgage origination. And our alternative hypothesis is lenders become more concerned about the climate change and its potential impact on local housing market after experiencing the abnormally high temperature. So here is our empirical methodology, and we regress the loan approval rate and the loan amount on the temperature anomaly, and we control the state by year fixed effect, county fixed effect. So here is our main result. When we regress the loan approval rate on the temperature anomaly, we find the temperature anomaly significantly reduce the loan approval rate. And when we break down the temperature anomaly into 5 quintile, we find the result is driven by the warmest quintile. To further shadowize the channel, we explore the loan denial reasons for rejected loans. We expect that if lenders are concerned about climate risks and its adverse impact on underlying collateral, we expect the lower loan approval rate mainly due to the collateral reasons. Since the home database provides loan denial reasons for rejected loans, we construct the loan denials for collected reasons by the total number of loan denials for the collected reasons skewed by the total rejected loans. And we find the coefficient of temperature anomaly is positive, indicates that the temperature anomaly increases the loan denials for collected reason, which confirm our prediction. We also replace the approval rate by the total loan amount and find the result consistent with our loan approval rate result. We further test the impact of temperature anomaly on the loan interest rate, and we find the result is insignificant on the loan interest rates, which is consistent with the literature that loan pricing is driven mainly by the computerized algorithm that rely on hard information with relatively little input from loan officer. We also conduct a bunch of robustness tests, and due to the time limited, I will skip this part. And the major challenge, as I mentioned, the major challenge of this paper is to disentangling the credit demand and supply channel. And I will skip this part as I have already mentioned, and focus on the placebo test using fintech lenders. So here for fintech lenders, the application and review process for mortgages are almost entirely conducted online, and no human loan officers are involved in the decision-making process. As a result, if temperature anomalies affect mortgage lending through its effect on local loan officers' climate change belief, we should find no results for loan originated by the fintech lenders. On the other hand, if the effect we document is due to unobserved reduction in demand for mortgage in areas with abnormally high temperature, we should find a similar negative effect for fintech lenders. So here, this figure plots the coefficient of the regression result. We find the positive effect of temperature anomaly on fintech lenders, which is inconsistent with the demand channel, but consistent with the literature that the fintech lenders partially fill the credit gap left by the traditional lenders. So the underlying mechanism we propose is that lenders' perception of climate change increases significantly after people personally experience unusual warm weather, and they take actions on reduced lendings to the local housing market. And consistent with our underlying mechanism, we find the consistent evidence. And we also conduct the diff test relying on the Cosemans nature experiment surrounding the release of Stern Review in October 2006. Stern Review is one of the earliest and most well-known analysis of economics of climate change, and likely significantly raised public awareness of climate change. And it is unlikely to change the physical risk of climate change. And according to the Google SVI data, we could find that after the release of Stern Review, the attention to climate change substantially increased. And here is our diff analysis, and we find that after the release of the Stern Review, the coefficient of temperature anomaly is substantially reduced on the loan approval rate as well as loan amount. So here
1
is
minute
the
left
conclusion of this paper. And thank you.
Yes, you can continue. 1 minute left. Yeah.
Okay. So I just want to emphasize the important policy question induced by this paper. Will the predicted rising temperatures and the extreme weather events lead the society to reassess climate change risks and invest more resources in mitigation and adaptation? Okay, that's all my presentation. Thank you.
Okay, thank you so much. And now let's see the question for you. It seems like I may have a question for you.
Okay.
Yeah, sorry, I thought you said you have a question. Well, thank you for the presentation. I think it's a very interesting paper, and I think it's a very natural setting to study this question, because I think at least until very recently, people have not paid too much attention to physical climate risks, and I think housing makes a lot of sense to study these risks. I have a bit of a speculative question. So you are aware of this paper by Amin Uzat and Matthew Kahn about where they show, I think you even cited it in the presentation, where they show essentially mortgage lenders create mortgages to risky houses in terms of sea level rise, and then they shift this risk by selling it to Freddie Mac and Fannie Mae, right? Which would then imply to me that they wouldn't really care about this in terms of mortgage rates, because they can just get rid of the risk very easily. Freddie Mac and Fannie Mae doesn't put any regulation against this. I would ex ante expect them not to care about this so much. So in the face of that fact, how do you reconcile your findings with that? That's what I wanted to say.
Yeah. Okay. To avoid the potential impact of the securitization of the mortgage, when we construct our loan amount proxy, we exclude those loans to other institutions.
That makes sense. But again, I mean, I guess one nice thing in your paper would be to also include those in your results and try to see like when we add these down, they're less, the results are less strong, or perhaps even this could constitute a placebo test for you, right? Where you could say, see, like those do not make sense.
Yeah, thank you for the suggestion. Actually, we have done the test, and the magnitude and the significance level are consistent with what we have now. The impact is very minor.
I see. Okay. Then that's good to hear. Like, if I was a referee, not that I would be, but I think I would like to see that.
Oh, thank you. Hope you will be my referee.
Okay, and thank you so much for Tinghua's your presentation and today. And since there are no more question for you, thank you for. Oh yeah, question 3 now it's coming.
Yes, this question seems to be directed at me.
Yeah.
So I'm sorry to take over, but I will just give a brief response. Yeah, so wouldn't temperature-based measurement of vulnerable portfolios have transition risk in there as well? Yeah, I fully agree with that. I think I actually read that in the Volatility Risk Institute by Robert Engel and co-authors, they actually do something where they also correct for a transition portfolio. So then they kind of try to take out of the transition risk and just focus on physical climate risk. So we haven't done that because we hadn't really thought about that back when we were making these portfolios. But this is definitely something to take into account if we look at this again. Thank you for the comment.
Hello, Tinghua, are you there?
Oh yes, I'm still here.
Okay, now you can answer the question.
Who asked me the question?
Okay. So...
I think the question is to the first paper.
Oh yeah, so I just gave a brief response.
Yeah.
Yeah.
Okay, that's good. Okay. Okay, thank you so much for Olga's presentation and very interesting topics. And if there's no more questions, and so let's give an end. Thank you.
Thank you.
Yeah, thanks for the opportunity.
Thank you and good luck.
Bye-bye.
Bye-bye.